third speaker today, Verband Subbarao. Dr. Subbarao holds his PhD from Imperial College in London, and he has a Master of Science in Engineering from the University of Michigan, not so far from Ohio. He has 35 years of experience as a bridge designer, has been responsible for the design of many landmark bridge projects in India. He's also a forensic engineering expert on bridge failures. Subbarao will also assume the office of President of the International Association of Bridge and Structural Engineering starting the 1st of November. So you're taking on another big job. Thank you for that. He tells us that in earlier years, he was an active mountaineer with 7 Himalayan expeditions. I don't think anyone else can claim to that in this room. Would surprise me. To his credit, now he has become an avid sailor. Thank you for your presentation.
Yes, whilst we wait for that to start, I want to thank Mike Schleich and Vision and Construction for inviting me here. I'm absolutely humbled to be in this hall of greats with some of the greatest engineers of our current time. And I'm delighted. I bring greetings from India, from a legion of Mike and Jorg's friends and followers and colleagues, and also from the ABSE. So my topic actually today is on India's quest for bridge engineering excellence and what challenges and developments we face. I would say we're about 10, 15 years, between 10 and 15 years behind China in terms of our growth story. Yes, so you see here some of the traditional Himalayan bridges. The one on the top is the Living Roots Bridge, and the roots that have been stitched together to form a bridge, which you see on the top right passage, crossing a simple Himalayan log, and what we call a tar in the middle, which is a wire by which you pull yourself, a pulley system by which you pull yourself across in a basket, and of course the well-known suspension bridge. Using appropriate technology is very important. Bamboo is lots of bamboo and varieties of bamboo in the northeast of India, and you see some expressions of beautiful bridges from the northeast. Mumbai, the city in which I live, has this wonderful oily bander sea link. It's a sea link, mind you, offshore. And my presentation will focus on a small introduction. SPP is tryst with Indian Bridge Engineering, that's Schleich, Bergman and Partner. Examples of Indian bridges, which I'll rapidly push through, and some thoughts on what matters today and future needs and challenges. So infrastructure is not about concrete and steel, but about improving people's lives and creating opportunities for growth. And this is where India finds itself today. With one of the highest GDPs in the world, India's growth story is largely funded by massive investments in infrastructure projects in transportation, power, and communication. The huge trust on transportation infrastructure is one of the key drivers of GDP of the nation. So this presentation, I will speak about collaboration with German and Indian consultants, some landmark projects covering road, metro, and pedestrian, and India's pursuit for excellence by its significant achievement in modern technology and materials, which give it a lot of confidence going forward. Though we face many other issues like environmental issues, construction quality issues, and logistic hurdles, India is a complex country. It's so huge. It has a long coastline. It has the high Himalaya. It has the Indo-Gangetic Plain with foundations being very, very deep, and a complex terrain, complex geography all across the Indian continent. So how to build resilient infrastructure in these days of climate change are something that has taken us today, taking a very important turn for us today. And in closing, I have some thoughts on the post-COVID context and the rapidly evolving AI era. Urbanization is a huge thing in India. You can see on the top left the increased urban population versus the rural falling off. And we're talking about the largest population in the world, of course, in my country. And you can see the huge road building program in the middle, where in the last 30 years, from 70,000 kilometers, we've added 161,000 kilometers and growing at the rate of 30 kilometers of road added every day through various government programs. 22 cities have metros. In my own city of Mumbai and Greater Mumbai, I have 26 metro constructions under construction, of which 6 are about to start in the coming few months. So 20 are under construction. And you see on the bottom, since it's urban congestion, there's so much congested corridor, you don't have enough road width, so either you go out to sea, so we have a whole sea link and a whole coastal road, what we call in Mumbai, to take the pressure off the existing road network and put it out to sea signal-free to reach up to 60 kilometers, 70 kilometers along the sea without any signal in the current planning. Of course, it means a lot for sustainability, low carbon footprint, of course. And you see here in Chennai, a city in the southern part of Mumbai where you have a double-decker construction. The metro is actually double-decker, it's level 2, and the road is, an additional road is at level 1. And so you have double-decker on an existing road that you have in the city, just simply because it's not possible to, these are cities which exist, and there's no space, so you just go double-decker. And there's so many double-decker constructions in India at the moment. Metro and road, road on road, and so on, 2-level. The road network was one part. The rail network has hardly added about 10,000 kilometers in the last 30 years, but it's in difficult terrain. What was easy to have been done had been done. Now we're doing the really challenging ones, and this is taking a huge amount of effort and energy. The city in which I live, we are on an island city. Mumbai is an island city, and across, on the far distance, you see it fading away, right away where the bridge keeps going in and disappearing on the right-hand side. 22 kilometers long is what we call the Trans-Harbour Link, the Mumbai Trans-Harbour Link. It connects 2 ports, and it connects the island city to the mainland of India, and it has a huge implication for, when we have any disaster in the island city, it gives a very good escape route, and it is built with high resilience, again, for the same reason, for a higher seismic level and a higher wind condition, and so on and so forth. So this link is vital for the city, and it allows the pressure on the city, the population to move, build the city across the water, and it's 22 kilometers. It takes exactly 12 minutes to cross this. So the whole city, and the new airport of Mumbai is coming up at the end of this bridge. This side, I'm in the city. The far distance where it disappears and it got the ABSE award. And of course, it's collaboration. It's collaborative effort, and the collaboration is amongst various countries for such a landmark project as that. Now, I want to tell you the story of 2 families, that Schleisch family and the Subbarao family to which I belong. Our fathers, Tien Subbarao and Jörg Schleisch, and me and Mike. So this is the story of, you can track the history of bridge development in India through this, and you can see this bridge, which was commissioned in 1989 in the Kingdom of Sikkim at that time, before it became a part of India. It's just a 77-meter, a simple concrete deck, but the Bauhaus culture reflects in this bridge. It uses local technology, it uses local material, and it builds and transfers technology and improves the lives of people. It identifies with where it belongs. And this place had no roads at that time, very narrow roads, and you could not take lorries there and so on. So the cables were actually wound at site. The parallel strands were wound at site. The taping was done at site, and I'm happy to tell you that this bridge, where you can see them, doing the greasing and all the taping, etc., and parallel strand is still in use and in very good condition. So that's what appropriate and a Bauhaus thinking gave us right then. I didn't realize till I heard the lectures yesterday the importance of thinking in this concept of Bauhaus, but maybe it came naturally to Jörg and my father at that time. My father was a contractor for that bridge at that time. And then you move along, and a bridge that took 20 years to build, had it been built at the time it was in those 3-4 years, it would have held the world record. A huge jump in the world record to 457 meters main span. The 457 meters never happened. Many other bridges, it never got built in that time and got the record. Many bridges overtook it in that time. But this is a reflection of how local labor, local politics, local constraints, which are very difficult to foresee, actually slow down projects, and to win against such odds is itself a great feat. It's not only a feat of engineering, but it's a feat of achievement. And the Calcutta city in which this is it's one of the landmark and icons and very much loved. So it's a 457-meter main span, and it set the concept in the entire world. For the first time, the ladder construction was created, and you see the edge beams and maybe a secondary middle longitudinal beam, and the ladder construction was developed by which you could build above the water, and you could put in concrete, either cast in situ or precast concrete decking, and create a very simple bridge without having to worry too much about it. It's a very simple, lightweight crane, which you see in the left. So you see the light triangular derrick. It's a simple derrick which was used to build this entire bridge. So this is appropriate technology for you. And identifying with what the local concept was. No HSFG boats exist in India at that time. The rivets were very well known. So you see in the bottom out here, rivets being used to create this bridge, and the local gang force, and these hot rivets so that we could create the joints. There's no welded joint and no HSFG bolt joint. It's riveted. Again, appropriate technology. Move forward again, commissioned in 2007, is the Nivedita Bridge, which Mike touched upon yesterday. It was India's first multi-span exodus bridge, and you can see the segment being lifted above the Ganges. India has huge rivers, as does China, and we have bridges which go 22 kilometers long, 12 kilometers. It's quite normal for us to have more than few kilometer long bridges across the Brahmaputra, the Ganges, and their tributaries. It culminated in the recent time India's most modern bridge. It is in the shape of a namaste, the welcome symbol of India, which is namaste, and it welcomes you to the east of Delhi. You see the east of Delhi rapidly growing and developing, and you see the welcome namaste of the two towers, taking again an idiom from India and converting into one of the most beautiful structures we have, and an iconic piece, modern day India, reflecting the aspirations of modern India. And you see here the construction as it was being done, and you see the team. You see on the far left there, you see some of the engineers from the department. You see my father, Jörg Schleich, Mike, the engineer, Joe Skurian, and myself here. And at a later date, here you might recognize Matthias Widmer and the architect, Ratan. So this is collaboration, and this is the team. And the project was built, commissioned, as in very much in use. It has many, many achievements, and it gave confidence. These three bridges tell us a story about transfer of technology, tell us a story about two families, and tell us a story about benchmarking India's achievement over time, and developing the most modern bridge is where I last left it. These bridges are very common. The balance cantilever with its drooping problem with creep and shrinkage being overcome with the modern day central hinge, rather than that plunger hinge. The central hinge is an isostatic structure, typically 2-span, 3-span continuous, then a hinge in the webs. And those hinges have been specially developed, and our understanding of creep, shrinkage, and the drooping of these family of bridges have been overcome with modern tools and techniques, and of course, understanding of material behavior over the time. And we have modules like this stretching. The longest bridge is 9.15 kilometers as we speak today. The largest exodus bridge, 144-meter modules, central span of 144 with side spans. And you see the vastness of the bridge, the rivers that we have to span, and how difficult it is many a times to construct in such terrain. This is the second longest exodus bridge at Ara Chapra in Bihar. It is 4.3 kilometers long, and it has typical spans of 120, 16 spans of 120. And this is 22 kilometers long, under construction, and will be completed somewhere towards the end of next year. And it's 22 kilometers long, again in the northeast of India with the mighty Brahmaputra River. A set of exodus bridges for you. We have 214 bridges built or under construction, and 26 more are being added by the end of this year to bidding stage. So you can imagine the rate at which, from where we were and where we have now gained our confidence, and many Indian bridge engineers today are able to do these quite easily, which happened over time with the transfer of technology and from foreign consultants and foreign contractors. And we absorbed that, and we learned, and we improved, and we go ahead now. So you see here this bottom one, which is a very important concept. In the Himalayas, the roads are on each side in cutting. There's very unstable slopes, and you don't have much space to develop a good turning radius. So you have almost an L turn at this point. So we took a cable stay bridge, put a pier there, took a simple, exodus bridge with a short tower, and we kept the rock anchored cables at the back so that the vehicles can turn below it and go across. So these are ways in which we need to innovate in such difficult terrain and complex geology. Again, you see here the fourth longest and bottom right, India's longest, and a curved, highly curved cable stay on the top right hand, and a five pylon cable stay with a huge lookout observatory in the middle over a lake in the bottom left. So these are examples of built, the top one being 350-meter main span on the left, the bottom one, Bet Dwarka, India's longest span, being 500 meters, and a 700 meters bridge is being completed at the end of next year with an orthostropic deck. So that's the bridge. It joins a temple on the other side. There's a huge pilgrimage, so the walkways are very important. The walkways are covered canopies, and there are solar panels on top. The bridge gets its own electricity from that, and the powers itself, in fact. And the huge amount of pilgrims that happen in the annual season are a key feature of this bridge. And the island was, from the mainland to the Dwarka island, there was only ferries, and so many people want to go, so we made this bridge. And it has a typical peacock feather you see out there, a tall, the Indian national bird. And the lighting that you have and the beauty of this bridge when it was being constructed, you can see the peacock feather there. Some examples of, I'll take you back. Of course, the pylon using jump form being constructed in deep water over a piled foundation. You can see the piles below at the bottom. And you see the way in which prefabricated segments were being lifted up and put into place. And again, it is ladder construction, which was invented in the second Hooghly Bridge. A future look, a process under bidding, a hybrid suspension cum cable stay. And you have a lower deck here with the walkway, and you have glass on the other side. And these are trusses at 6-meter intervals, which are integrated longitudinally by members. And these trusses are, of course, at the points where the cables come in, and it gets its torsional stiffness and its tremendous stiffness, obviously, from these trusses interspaced at 6 meters. It's a 2-level, again, a pedestrian, and it joins 2 temples at a high. So the 2 temples are part of a pilgrimage again, and people would have to come down, go across, go up the other hill, etc., and this whole thing took 4 hours. When this is built, it will take only about 5 minutes. So again, you see here a 1914 open span of a bridge, which was a Sheza span, a 1914 opening bridge on the Indian Railway to the island of Rameshwaram. Actually, that bridge allowed India to be connected to Sri Lanka with a small ferry. We could reach Sri Lanka in very quick time. And when it was washed away, the network was washed away, all that remained was to that island of about 3-4 kilometers, this old 1914 bridge, which still operates quite well. But given condition, we got a lifting span parallel to it, and the railway was diverted onto that, and the road bridge parallel to it, which you see here, and the bus on it. This is a lifting span, and it replaces this 1914 bridge. That's the Indian Railway for you. The Indian Railway, again, this bridge, which I was the designer of, it's only about 4.4 kilometers long. You can't see the horizon on the other side of the Ganges if you stand on this side. And it was built using overhead cranes and triangulation with an overhead crane. And it's built on what we call well foundations, double D well foundations, which is unique to India. This concept of founding it well foundations is a very, very unique concept in the world to India. Though I shan't have time to speak about it, this is riveted joints, okay? This is riveting again. Railway are very reluctant to go to bolting because of fatigue issues. And all the members here, cross members here, all the joints, all the gusset plates are actually riveted, okay? And this is a modern bridge. It carries 25-ton rail loading, and it has 3 lanes of national highway on top. And at the same time, Indian Railway took a bold step ahead, and they went for a fully composite truss. You see the road on top, and the normal simple truss, and 123 meters both, but that is riveted. This is fully welded and fully composite. So this is a quantum leap for the railway in India, and the bridge is functioning well. Another railway bridge on the very difficult Himalayan terrain, very steep slopes, unstable geology, etc. Lot of improvements to the rock, and you can see the huge amount of unstable conditions that had to be overcome. And this 1.3 kilometers bridge was push launched from one side to the other side after we used this crane, the highest cable net, largest cable net crane in the world, with this device to actually lower and lift and build up this whole arch. So there's no staging possible, of course, in this deep ravine. And wind is terrible, funneling effect of wind is terrible, seismic zone 5, unstable hill and slopes. So this speaks volumes and confidence for bridge engineers in India. Anjikat Bridge, a bridge that's in India's first cable stay on the same line. And again, you see a crane being used, very difficult site condition, to launch a bridge across using simple rope blocks and rope winches. And you see the stages, the bottom, left, right, and finally in place there. Simple technology, but very important. Sustainability being addressed. An old bridge, a 4-kilometer long bridge, its piers were cut off and integrated, redeveloped, and the old concrete bridge, which had that drooping problem which I spoke about of balanced cantilevers, was repurposed and reused. And I think this is a very fine example of addressing sustainability. Reuse of the entire bridge's foundation and substructures, and putting a lightweight steel structure on top to relieve pressure on the foundations also. And this is a real live example. In some cases of the first UHPC bridge in India, and now the longest UHPC FRC bridge being built in India with tub girders. It's 2.5 kilometers long and be completed at the end of this year, middle of next year. Kites derive the inspiration for this beautiful pedestrian bridge, Festival of Kites in Ahmedabad city. Here, the tamkura, a local instrument which you play by leaning on your shoulder, much like a sitar, giving the inspiration for a pedestrian bridge. And I will just quickly skip through these 12 foundations that I wanted to talk about and come to what matters most, because there is very little time. So the key priorities for Indian structural engineering fraternity today revolve around creating a more sustainable, resilient, and technologically advanced built environment. Adopting asset management strategies that address increasing urbanization and the increasing scale of climate change-induced hazards. We need to focus on climate resilient design, which is not being done at the moment. Reduce the embodied carbon in planning and design. We don't have anything yet on how to do it. And using innovative materials for structures and adopting a new circular economy with repurpose, reuse, reduce, and recycle. I just showed you a few examples of doing that. And we have some challenges. Structural engineers have a very important role to play in sustainable development of the built habitat. In order to do so, structural engineers need to take a more dominating role in the decision-making process. We find ourselves not involved in policy in the decision process. This might be a malaise in many countries, but in India it's very pronounced. Presently, they're playing a subservient role, the Indian structural engineers, to the architects who dominate. And this needs to change to become more collaborative and become more cooperation between these two, in fact, between multidisciplines. And engineers need to, again, play a leadership role. The leadership role can be played by structure only when the academic institutions and the industry work collaboratively to prepare them and position them in the leadership position. So this is lacking in our education. Structural engineers must have good communication skills, good interpersonal skills, and also have a wide knowledge on multidisciplinary subjects, as became obvious in yesterday's lecture by Mike, in addition to their core subjects. They should be trained to be learners throughout their career. There is in India, many countries, I know Ian is here. Ian, you have the engineers bill in the UK. You have a regulatory body. In India, we don't have a regulatory body for the engineering profession. This might be true in many, many countries elsewhere in the world. So there is a crying need to get an act of parliament passed to get the engineers bill, and that will regulate the profession of structural engineering, in fact, all engineering in India with a regulatory body. And of course, there's been talks about AI and what it brings in its wake. Is it a two-edged sword? What the threats and opportunities, we saw that in the earlier lecture. The threats and opportunities, one is, of course, of becoming obsolescent. Are we going to be a nobody? The cognitive skills are being enhanced. As we speak, it keeps enhancing its cognitive ability, that which we zealously guard about, for ourselves, and which was addressed in the morning meeting, that is that of the mind in its own spaces, are becoming more and more into the AI world. So the cognitive ability of AI is increasing day by day, and at some point in time, it won't be a question of us or them, it'll be a case of we. We will have to coexist. There is no question at all about that, and we need to leverage that. And maybe it'll free up a lot of time for us to sail and mountaineer and, play golf. And it may, it might free up a lot of time. One can't say what the future holds. But if cleverly used and used in a matter of collaboration and cooperation, much like a Bauhaus thinking, I think the culture may then stay, and we may have a coexistent symbiotic living with AI. So on those, thank you very much.
Thank you. Any questions?
I have a question which is related to your presentation on innovative structures, and I would relate it to Professor Mike Schleicher's presentation on innovative materials, and the innovative material is CFRP. So I would like to ask if CFRP has arrived among the structural engineers in India, because I know that from...
I'll answer that question even before. I've done 40 bridge repairs with CFRP, and I have just written the guidelines for India with a set of colleagues from IIT Hyderabad and elsewhere, and from Russia and from the UK. We've created a guideline, and it will be published pretty soon. So yes, we are ahead of the guideline, and we're using it in a large way.
And also as a principal material? Or
we use CFRP, and we use fiber and wrap, as is common elsewhere. We use CFRP wraps. We use the ACI 440 and the FIB 90 guidelines at the moment, but now we develop our own.
Thank you,
Thanks.
sir.
Thanks.
More questions? I thought it was kind of interesting that you showed a juxtaposition of very old technology, riveting. You said the rail is hesitant to use bolting. Why not welding? Or you showed some bridges with welding. How does this tradition last in India, the riveting?
Now, rivets are hot, you know. They're banged in from both sides and created. There's no gap in the mating surface of the gusset plates and the members. It fills that completely. And this has huge implications for long-term fatigue. And with railway loading, fatigue is the main design parameter. And the railways were very, very reluctant to switch away from what was a time-tested, working thing to something which would change their mindset. And it's only recently that they switched to HSFG bolts, and only recently that they've made a fully all-welded steel composite. All joints are welded. So this is the reason. And railways still are having riveted construction even today as we speak, just for addressing this matter of fatigue. They're reluctant to change.
Are you also planning on health monitoring, for example? No? You're building a lot, well, in Asia, especially Africa is also coming. How about monitoring the new structures?
Oh yes, structural health monitoring, you mean, yes. I forgot to tell you, for example, Signature Bridge has a monitoring, of course, a very advanced monitoring system. Now it's mandatory for major projects to all be monitored. The Trans-Harbour Link has continuous structural health monitoring system for stress, deflection, wind, environmental parameters, and everything. And you have that even for the performance of the paint, it's monitored. It's a C5 paint, which we use on the Trans-Harbour Link, 30 years guarantee. So even paint is monitored. And yes, monitoring is now here to stay, and we are gradually building it into all our projects. It's been there for about 15, 20 years in India easily. Many railway bridges are monitored as well. Not the small ones, but the larger projects, yes. In the tender documents itself, you have to bid along with a full structural health monitoring plan and program. Yeah.